Okay, in the fourth lecture for chapter 20, I guess, well, first thing I want to remind you of something. Voltaic cell, um, electrons flow from the black, from the anode, and then they're dumped out onto the cathode on the red. Remember the reduction reaction here occurs there, and the oxidation reaction occurs there. Now, this particular presentation, what I want to get at is a little bit more of a understanding of how we can tell whether the thing is a spontaneous reaction. And actually, we see one of the key features on the voltmeter here. That's a positive value. So, when you see a positive value on the voltmeter, or what we'll do is we're going to calculate the EMF, or remember there's another notation for it. It's the Enol Cell, the voltage that is generated by two half reactions at standard temperature and pressure, 1 molar concentration. I'll mention that here in a second, or talk more about that here in a second. But when you see that positive value, then it tells you that the phrase I'm going to use, that the reaction as written is going to be a spontaneous reaction. And that's the first problem I'm going to do in just a minute. But one other feature about this particular presentation is moving away from non-standard conditions. And again, my label for that is non-STP. And specifically, what I want to talk about is when the concentrations are not at 1 molar. So, probably just looking at this solution, this is pretty dark blue. I'm guessing it's probably at 1 molar. Actually, I know this is at 1 molar concentration of the copper +2 and the zinc +2. How do I know that? Well, I know that because I get the 1.1 volt reading on the voltmeter. We calculated that in the second presentation. We were using the standard reduction potentials to calculate that. So I know that these two are at 1 molar concentration, standard conditions. So we are going to extend our abilities here and go beyond or usually lower than the 1 molar concentration. And also keep in mind that really anytime you start talking about spontaneity in chemistry, you can't get away from the subject without dealing with Gibbs free energy, because remember that is the measure of spontaneity for a chemist. And if Gibbs free is negative, then that tells us that we do have a spontaneous reaction. And so we'll tie chapter 19 into this chapter with a few problems as well. The first thing I want to do, though, is I want to break down one of these redox reactions to predict whether a reaction is spontaneous or not. And so it's giving you a hint in terms of what we have to do. We want to use the standard reduction potentials in Appendix E to determine, which of these are spontaneous and which are non-spontaneous. And remember, the use of the standard reduction potential begins with this particular equation here, where you're just subtracting out the two reduction potentials to predict or calculate the EMF for the cell. Now, to figure out what's going on, which is the cathode and which is the anode, and to pair it up with the half reactions on in Appendix E, well, what you have to do is you have to take one of these equations, and I'm going to do this one specifically, and break it down into the oxidation and the reduction half reactions, so that you can more clearly see where what reactions are happening at the cathode. Remember, that would be the reduction reaction, and then the oxidation reaction is happening at the anode. And if you can identify which is the Leo and which is the Gur, in here, and then pick them out on this chart, then you're just plugging and chugging into a fairly simple equation to calculate the Enol cell. And then if this is positive, that tells us ultimately whether we have a spontaneous reaction or not. Okay, let's break this down. I need more room than what that PowerPoint gives me. Now, when you look at one of these redox reactions, this thing is already balanced. what I would recommend doing, and what I do, is I focus in on what's happening with a particular metal. That's usually the easiest thing for me to spot, and I see very clearly that the copper is being it's being reduced here. It's gaining the electrons. So if I just sketch out the half reaction, okay, so this is the GER. So I already know what is happening at the cathode. I know this number. You know, it's the reduction reaction as written. You take the value that was in the standard reduction potential chart, and I already have, this would be the standard reduction at the cathode. So I already have this particular value just by picking out the metal and what's happening to it in the balanced equation. Don't worry about waters and hydrogens or hydroxide. They'll fall out when you start using this chart here in a second. What you want to focus in on are a couple of I guess, how do you say, the other species, the other chemicals that are in the soup, and that's actually where I'm going to begin in terms of trying to construct this particular half reaction. Now actually, I know this one has to be the Leo. You know, this is the oxidation reaction, so it's going to be the electrons are going to be on the product side when we sketch this out. And I'm actually going to use the standard reduction potential chart to help me out in terms of what this half reaction looks like. Because whether you're given a redox reaction to balance or you have a balanced redox reaction, that redox reaction that's being described, it's going to be composed of two half reactions. Those half reactions are going to be able to be found in these charts. So, technically, you could actually use these charts to help balance out redox reactions. Now, I will tell you that on the test, you're going to have you'll have information from the standard reduction potential chart, but you're not going to have enough information to balance out some of the redox problems on the test. So you're still going to have to balance the redox reactions the old-fashioned way, not sort of the cheat, if you will, that I'm doing here. And what I'm looking at here, so how do I do this? I know this is an oxidation reaction, so I know the electrons, a certain number of electrons, which I don't know at this point, are going to come out on the product side. Well, like we've said before, like we've seen in the two presentations, on the standard reduction chart, the electrons are always on the reactant side. So just like I did in the second presentation, whenever I'm dealing with the oxidation half reaction, then this reaction is actually reversed. And so if I'm trying to find this half reaction that's from this balanced equation, I'm going to look on this side for the reactants in the oxidation half reaction. There's iodine, there's water, and there is the iodate ion here. And so what it does, I see that, okay, so iodine is going to be paired up with 3 water molecules. The iodate has 6 protons, and then I have 5 electrons being kicked off here. And that's really this is all I need to be able to figure out the EMF for this particular cell. And let me, so what I know now, I didn't put the numbers here because I wanted to save some room, but the standard reduction potential value for this particular reaction, let's see, is a plus 1.200 volts, and it would be shown, on the right hand side of this equation if I had the full chart here. And really, I have the information now for calculating the EMF. Let me just go ahead and do that. And what you'll see is that this is actually a non-spontaneous reaction. So that's what's happening at the cathode, coming from the reduction half reaction, minus the 1.20 volts for the the oxidation half reaction, we already see that the potential reduction potential here is greater. And so with the subtraction process you're going through here, what it tells us is a negative value, and this reaction as written is non-spontaneous. Now, what does that mean for us in terms of constructing a voltaic cell, constructing a battery? Well, all that means is that if we were wanting to use these chemicals to produce a voltage, we would switch the order of the reaction. These would be the reactants, these would be the products over here. So we would essentially perform the reverse reaction here. And the voltmeter, when the electrodes are connected properly, would then give a positive value for that one. So it's non-spontaneous as written, it's spontaneous in the reverse process. Okay. And like I said, that's really as much as you need to do for this particular equation, but I want to go one step further and just sort of fill in some gaps here. And specifically, what I'm talking about are the molar coefficients up here in the balanced equation, because you don't see a 5 here, you don't see a 6 here in front of the water. If you think back to how to balance a redox reaction, if you broke down these two half reactions, you saw 2 electrons here, 5 electrons here. What's the lowest common multiple of the two is 10. So I would need to multiply that half reaction by 2, and then this half reaction by 5 to balance out the equation. And actually, I just noticed a typo, and the typo is coming from the textbook, and actually, I paused the video and I looked at another textbook for this, and actually in a different textbook there's actually a 1/2 in front of the iodine in the half reaction, and then everything would actually work out. So there is a typo, and I'm going to say that Brown LeMay's typo is in the chart there. So it's a big textbook. There's always that chance of there's errors in all textbooks, so just be aware of that. Okay, so it's just a little practice, and I'm going to go ahead and tell you that, well, I'm not going to do the other two. I'm going to leave it up to you to figure that out. I guess I'll go ahead and tell you the answer. Both of them are spontaneous as written. And so if you break, let me give you a little hint. And again, I would concentrate, there's a metal, that can establish what the mercury is the one that's gaining electrons, so it's going to be the GUR, it's going to be the cathode. And then on this side, I would, again, I like looking at the metals, because a lot of these redox reactions, you're going to have at least one metal in the equation to focus in on. And here you see that the manganese is actually being oxidized, so it's going to be the oxidizing half reaction. And so, what does that mean? That means that the sulfurous acid and the sulfur has to be involved in the reduction reaction, and that's going to be that's what's happening at the cathode. And so break it down a little bit, but I would suggest practicing on that one. Now the spontaneity. Yeah, we can talk about a positive voltage on the voltaic cell, and that's true, that works. But like you've probably noticed, in terms of what I'd like to talk about with spontaneity, is this Gibbs free energy. And here is an equation that links the two chapters together. This is referring to what's happening in the voltaic cell. There's the EMF there. The N is actually representing the number of electrons that's actually transferred, which is important. And then the F is, well, there we go, it's Faraday's constant. And all it's doing here is it's relating, what is the unit of energy with respect to the voltage that you're going to see, or that's being produced per mole of the electrons that you're that you're transferring back and forth. And so what you do on these calculations is well, in this case we have a balanced redox reaction. We have to break it down just like we did on that last example. Use this to calculate the standard EMF, and then the naught here are important. The naughts here are important because it establishes STP for both calculations. And if this is a positive, then we should see this as a negative. Remember, that's what we see for spontaneous reactions, and I talked about the negative Gibbs free energy in chapter 19. Just another word about the Faraday's constant. Whenever you have joules per volt, that's actually a unit called a coulomb, and that's a unit of charge. This value here, 96,500 coulombs per mole. That is the amount of charge per 1 mole of electrons. And so the reason why they change a unit here is because, when you plug it into this particular equation, well, it's going to allow the units to cancel out, and we're going to left with joules associated with the process, which is the unit for Gibbs free energy. The Enol cell is in volts, so the volts are going to cancel out, and you're going to left with joules. So the book doesn't give a very involved description of this, but it does talk about the amount of charge per 1 mole of electrons. This expression here, the book doesn't do very much with it, but if you look at other textbooks, the way they construct this particular equation is they talk about the Gibbs free energy as and I talked about it in class a little bit. It's the maximum amount of work that can occur in a system, and it's related to the EMF and the electron flow for that voltaic cell. And so some textbooks do go into where is this equation coming from, and of course for this class I'll do that occasionally like I'm doing here, but it's not necessarily something I'm not going to have you derive some of these equations. If you want to do that, take physical chemistry. You'll have plenty of practice there. What I want to do is use these equations to answer these types of questions that are very typical for Gen Chem 2. And there's 3 here. There's the number of moles. And remember, this is an important point. Whenever you see N in these equations from this part of the textbook on, and this is section 20.5 in the 10th edition of Brown and May. But when you see N, that is referring to the actual physical number of electrons that are transferred as the reaction is written. Why do I mention this? Well, back here, it doesn't matter how many electrons are transferred. We just took the value off of the standard reduction potential chart and plugged it into the expression. But the actual number of electrons that are transferred, 5 times 2 is 10 electrons, and then 2 times 5 is 10 electrons. So, like in this particular process, N would be equal to 10 electrons. And when you're calculating Gibbs free energy, it matters about how many electrons are transferred. When you're calculating Enol cell, you can just take the voltages from the standard reduction potential and then simply plug them into the expression. So just a little heads up when you start working on these types of problems. Now I'm going to break apart this expression, and I'm going to need some more room. Notice I do have the insert, the little portion. I picked out all the half reactions that's dealing with chromium, since we have chromium up here. Now again, that's not what I'm going to focus in on initially, because thank goodness I have a metal in front of me. So that's that really helps to figure out what the 2 half reactions are going to look like. The only way to get from a +2 to a 0 charge on nickel is to add 2 electrons. This is the GERD. This is where the cathode is going to be. And this particular reduction potential value is a negative 0.28 volts. Now the other one, again, I'm going to ignore hydroxides, ignore waters, ignore protons. Now this is in a basic solution, so there's no protons, but the other characters are in there. So let's look at the chromium species in the reaction. And actually, since this is the reduction reaction, I know that this second one is going to be the oxidation reaction. I'm going to go ahead and put a number of electrons there. I don't know how many yet. And my guess is the water and the hydroxide are going to be associated with this part. You know, usually when you're looking at a simple electron either gain or loss from a metal, you don't need protons or waters or hydroxides. Remember, if you have to balance out oxygens and hydrogens with a redox equation, is when you start throwing in hydroxides and water. And you see, you know, oxygens and hydrogens in the two chromium species here. So just like I did on that first example, if I go to my chart, I can actually use that chart to figure out what the components are. And let's see, you know, this is the LEO, this is the oxidation process. So that means that it's actually the reverse in the chart, and that this is going to be the reactants for the equation as written. And we see the chromium trihydroxide and the 5 hydroxide ions here, and then there's the chromate ion here, and it has 4 water molecules, which is sort of what I anticipated, since, you know, water and hydroxide are in the balance equation, and this equation has 3 electrons. And then notice that this is off balance. There's 3 here, 2 here. You need to multiply by 3 on that one. Multiply by 3 on that one. Multiply by 2 there. And then if you transfer that all the way through the expression, then what you get, 3, 6, 3, you get the coefficients that you see in the balance equation. So, you know, it's in agreement. I'm happy with it. And again, what this is telling me, well, actually it's telling me 2 things. Oops, that is the reduction potential. I'm just going to transfer it here. It's negative 0.13 volts. And I'm taking it as written there. And so I'm going to use that to figure out the EMF of the cell. Remember, that's reduction that's occurring at the cathode minus the reduction potential occurring at the anode. The negative sign there is what that means is that it's going to flip this to a positive value, since the half reaction is flipped from the chart to the problem, to the example that we're looking at. And so when we plug those values in, we get a minus 0.15 volts. So the reaction as written is not a spontaneous reaction, which I'm going to make a comment about that here in a second. But first off, what I see here in the balance equation is that I've established the number of electrons transferred here is equal to 6. So you need to balance the 2 half reactions so that you figure out how many electrons are actually transferred during this process, because that's what's used in this equation here. There's the number of electrons. And you know, I said the EMF here is a negative 0.15. That's a non-spontaneous reaction, so you know, a negative here and a negative here will make this into a positive. And so the EMF of the cell and the delta G, the thermodynamic parameter from chapter 19, are in agreement, both telling us that this reaction as written is a non-spontaneous process. Now, to calculate delta G, well, it's simply just really you're plugging and chugging here. 6 electrons. Faraday's constant would be inserted here, and then the voltage for the reaction as written is 0.15. And so when you plug in Faraday's constant and do the calculation, what you get, and let's see, I went ahead and changed to kilojoules per mole. And this is a positive value. It's a non-spontaneous process. what's happening is that the voltage here is canceling out with the voltage there, and you're left with joules per mole. Now, actually, I want to extend this just a little bit more because there was another equation. Remember, there was a link between the Gibbs free energy and the equilibrium constant. This is a non-spontaneous process. That means that, well, I guess anything's going to go in equilibrium to some extent, shift to one side or the other. But if it's a non-spontaneous process, that means that the reactant side are going to be favored more than the product side. And so if I plug this value in, I would have to convert it to, just remember this R constant is in joules. So if you plug in delta G here, make sure to convert it back to joules. But you do get a equilibrium value that is very small. 10 to the minus 16. Oh, I'm sorry. It actually asked for it. Oh, so we're pulling this particular equation. This is from 19 material. Just remember, just make sure the units agree with each other when you plug this thing in, and then don't forget to keep that negative sign in there. Otherwise, it will be quite wrong. Now the next equation, the next calculation, the Nernst equation, very popular little equation, and what it is, when I look at this particular equation, I actually think about, this is a non-STP condition, and specifically, it's a non-STP in the sense of the initial concentration not at 1 molar, and you can see this is 4 times 10 to the minus 3. This is 1/100th of a mole. And so what it reminds me of is an equation back in the chapter 19, where you have Gibbs free energy at a non-standard condition. In chapter 19, we saw this kind of setup. We had the Gibbs free for the standard condition. Well, there's the EMF for the standard condition. And then there's this factor that has Q, the reaction quotient at initial concentration, that tweaks, that modifies the standard condition just a little bit. Well, that's what we have in this expression. But notice that there's the Faraday constant. Now, the Nernst equation that I would recommend you using is this one. It just takes a lot of work out of it. What this is still at standard temperature. So you get a 298 Kelvin here, and that's a lot of times what you're going to be working with anyway. If it's not specified, assume that the temperature is 298. And if you look at this expression now, R is a constant, T is 298, Faraday's constant, and if so all of these constants can be reduced to a single number, and then there is a change in the from the natural log to the log base 10. So there's a modification that way that varies that number also. But this is usually the form of the Nernst equation that I would recommend using. It's the form that I use. Because it makes the calculation much simpler. All you need to know now is the number of electrons that are transferred in the reaction for this portion of the expression. You don't have to worry about more calculation error with all these extra numbers. We still got to figure out Enol Cell the old-fashioned way, and this particular example, what it actually is referring back to a sample exercise in the book, and I'll go ahead and tell you in Brown and LeMay 10th edition. It's page 865 is what they're talking about. It was a reaction between aluminum metal and iodide in the elemental form of iodine. And so if we look, I'll just give the balance equation here. You got to break it apart. This one's a lot simpler, so I'm not going to spend a lot of time on it. But that was the equation that was talked about in that particular example exercise. And I'm just going to look at one of these. So you would break this thing down just like I did for these two previous examples. These are much more complicated. That's why I went this sort of long-winded explanation. Here I'm not going to do that. I'm just going to look at the fact that, well, again, like I said, when you have a metal in the mix, it's a lot easier to deal with. There's a 2 in front here, so that meant that this half reaction, if I was balancing the redox reaction from scratch, that means I would have multiplied by 2 all the way through, 2, 2, and then this would be 6. So what I'm doing here is just trying to establish what the N number is, how many electrons have been transferred. And then one other thing that the balance equation does is it tells me that this is a solid, that's a solid, and of course any kind of ion you see is going to be an aqueous solution. And so when you're setting up your Q expression, it's still products over reactants, but this is a heterogeneous equilibrium, so, or a heterogeneous reaction, so the solids here are going to drop out of the expression. And so Q in this one is simply the concentration of the aluminum cation raised to the 2nd power, and then the concentration of the iodide ion raised to the 6th power. Remember, the 2 and the 6 are coming from the coefficients here. So the balanced chemical equation is needed for these types of reactions. The balanced chemical equations, it not only affects the Q here and what we raise the different concentrations to, but as you saw in this 1/2 reaction, it tells us the number of electrons that are transferred between the 2 half reactions. You know, once we have these components together, then we're just plugging it into this particular expression. Now one thing that I'm going to do separate here is to calculate the Q value. So if I plug in, there's our concentration of aluminum and iodide. Just remember to raise it to the 2 power and raise it to the 6 power. And the Q here is actually going to come in as 1.6 times 10 to the minus 17. And so, you know, if in doubt of your calculator skills, practice, plug it in, make sure you can get this number, because now you're set up to oh, actually, my bad. There's one other piece of component. That's, I about got ahead of myself. I know that's it's not an unprecedented move for me. There, 2.20 volts. That was given in the sample exercise 20.6. They do it the same way we've been doing it over and over again. We take the standard reduction potentials from the tables to figure out this calculation. And then once we have those components, is we just, well, we plug them in. And then the log base 10 of 6 times 10 to the minus 17. And, you know, just like back in 19, this Gibbs free energy equation, you had the standard condition and then this little tweaking factor, if you will. You know, what's going to be what's going to be the deviation from the value based on the non-standard conditions is what you're looking at with both. I know it's real messy here, but both with this component and then this component in the 2 equations. And here what we see is we're actually going to increase the voltage just a little bit. 2 negatives makes a positive, and we get a total voltage of 2.37 volts. So I actually think about what we're doing here. We're at standard conditions. Remember, standard conditions. That's a pretty high concentration. 1 molar solution. I guess I'm thinking of perspective of like some kind of biological system. You know, 1 molar is fairly decent. You know, even the aqueous solutions that we use in lab, they're usually lower than that, lower than 1 molar. And in this example, you know, these are orders of magnitude lower than 1 molar, but you actually get a higher voltage that's occurring during the reaction. And what we're seeing here, without getting into too much of it, because we'll talk about it actually in the next example, this increase in voltage for this particular voltaic cell is due to the differences in the concentration of the 2 compounds here. That's what you see driving the reactions. Now the driving force for the reaction that's shown in this concentration cell is based on the concentration difference between the nickel 2 cation and the 2 half reactions. you know, this type of voltaic cell is different than the other ones we've seen, and the obvious difference is that the chemical is the same in each of these solutions. It's a nickel 2 nitrate in both solutions. This one's more concentrated than the other. And again, the driving force for pushing those electrons through the voltmeter is the difference in concentration between the two half cells, similar to what we saw in that last problem. Now, I do want to edit this picture just a little bit. And, you know, for this particular voltaic cell, it's giving you really all the information you need to know in terms of picking out these different components. Well, in a real problem, you know, like the next one we're going to see, we have the same cation in each half cell, but it's at 2 different concentrations. Okay? And this one's much more concentrated than the second one. And notice the first question is actually asking you, what is the anode of the cell? Okay, so when you're given one of these problems, you're not going to have it explicitly, you know, labeled like you see here. So I want to add something to this picture here, and I'm going to add a couple of marks here, pretend like they're alligator clips, and this one would be the black end, and then this one is pretend like it's the red end. And the reason why I do that is because, you know, when you have a voltaic cell set up in this fashion, black and red, and you get a positive value on the voltmeter, you know, if you have these things in front of you, then what it does is it tells you which side is the anode and which side is the cathode. And so what happens at the cathode? Well, the reduction reaction happens at the cathode. What happens at the anode? Well, the oxidation reaction happens at the anode. Let's sketch that out. Let's see what that looks like. So over here on the anode, what would be the oxidation that's occurring in this particular reaction? Well, the only option you have is that you have a nickel electrode and you have a nickel 2 cation in solution. So the only loss of electron half reaction that you could possibly have in that half cell is the one that's shown here, the loss of electrons. So and notice what it's doing. It's accounting for the label that they're providing for us, that there's a flow of electrons through the voltmeter from this side. And this is consistent with all the other voltaic cells we've seen up to this point. And again, I've added that additional label black, the black alligator clip over here, just to make it even more consistent with all the diagrams. And notice that this nickel plus 2 is different than this nickel plus 2 just based on concentration. So I'm going to add that subscript DIL for the dilute side of the voltaic cell. Okay, what is the reaction that's occurring at the cathode? That is a reduction reaction. That's a gain of electrons. Well, what can gain electrons? Well, it has to be that plus 2 cation gaining the 2 electrons that's being dumped onto the red positive end of the voltaic cell. And then what we would see is that there would be a precipitation of, there would be a buildup of the nickel metal on that electrode, while this electrode is eroded away. So please note, the chemistry is the same here. Again, the thing that drives the chemistry is the difference in the concentrations of the 2 cells. And just like for the anode side, for the cathode reaction, what I want to do is add the concentration term, or the concentrated. It's a strong concentration on this side. Okay, the reason why I'm doing this is because I need to build up the overall reaction of this concentration cell. And I do it just like any other redox reaction. This is a very typical look. Well, maybe it's not typical because you have the same metal involved, but it's typical in the sense of, the Leo here and the Ger is here. The electrons are going to cancel out. Something else is going to cancel out. Whenever you add up chemical equations here, well, if you have the same thing on the reactant side of one, and on this, and the same thing on the product side of the other, they're going to cancel out. Now, what we have is this overall reaction that I'll squeeze in down here. Conc going to the diluted one. So this establishes the overall reaction. And the reason why I do this is because, well, I'll go ahead and tell you, to work, well, actually, we saw that. There's the Q. You know, the reason why we're doing all this is because when we use the Nernst equation in this next problem, we have to worry about the Q. What are the concentrations initially? And to establish the Q, you know, we have to establish what are the products, what are the reactants, and the only way we can do that is go through this half reaction argument, okay? And that's, the book does the same thing here. It's section 20.6 in the 10th edition of Brown and LeMay. And so Q is Q, no matter what kind of chemical reaction you're handed. This is the initial condition. The dilute side is going to represent the product side. And so let's place that up here, and that's the, I'll put dilute on the outside. And then the concentration for the reactant, what represents the reactant side, is the concentrated concentration. So we're going to have the 1 molar down here and the 1 times 10 to the minus 3 moles up here to establish Q for this example. This argument that I've just gone through, this derivation of the overall reaction, and the determination of Q, it's all consistent with what the book tells you. So look at the book. It goes through the same kind of argument. And but again, I think it's helpful to actually sort of see the pieces come together in this format as well. And then, you know, when does the reaction stop? The reaction stops when both sides are equal in concentration. So again, that driving force is the difference in concentration here. As we go through the reaction, the concentration here is going to slowly decrease, and then this side is going to slowly increase until they're equal, and then you get 0 volts up top here. And now the electron flow has stopped. And this is, again, a standard setup for a concentration cell problem. Let's do one of these problems. And this one's this one doesn't have everything sketched out for you, so you sort of have to go through the logic required to figure out what's the anode, what's the cathode, what's the products, what are the reactants. And a very similar argument as before. You'll see some parallels. I think once you maybe listen to it once, look at the notes, you'll see some parallels between this problem and the nickel example on that last slide. Well, what I've done here and what I like to do for these problems is actually sketch out a voltaic cell and sort of go through the argument that I just went through on that last problem. And I haven't connected the wires here because I don't know which side is which. I want to make sure that I get the red and black side correctly. And as I go through it, I mean, I'll label it as to whatever I need to, actually, because the concentrations here are going to determine the flow of electrons one way or the other. But it's the same thing. The driving force in this voltaic cell that's described in this problem is this concentration issue. So I've kept, let's look at this. So the first half reaction has a higher concentration. The second half cell has a lower concentration, and that's what you see here. You know, what's the driving force? It's the difference in concentration. This one's going to drop, and then this one is going to increase over time until they reach some common concentration, and then the voltmeter will shut off. Our goal in this problem is to establish what this looks like. What is the which side is the anode, which side is the cathode, and then ultimately calculate what the potential for this voltaic cell is going to be. And we'll be using, well, our old friend, the Nernst equation. And so, you know, actually, before I go to that voltaic cell on the next slide, let me comment about the Enol cell. Well, a standard EMF here that they're wanting for this particular example, well, as it turns out, this is going to be 0 volts for any kind of concentration cell like you see here. Because remember what the standard conditions, it's standard temperature and pressure, yeah, even though pressure really doesn't factor in here, but standard pressure, temperature for sure for this example. And then also, the important point is the standard concentration is 1 molar. That 1 molar would mean 1 molar on both sides of the half cell. What happens? That means whether it's 1 molar on both sides, 0.5 molar on both sides, any concentration, if it's equal on both sides, then the voltmeter is just going to be 0. And so what happens in these concentration cells, like we have here, is that you have the same metal, you have the same cation, and at standard concentrations, the standard EMF is going to be 0. And so the Nernst equation is even simpler than the previous example. Because then all we have to worry about is how many electrons are transferred per reaction, and then this Q. What is this at initial conditions? Okay. Now one additional factor, of course, we need to figure out the anode. That means we'll be figuring out the cathode as well. We're going to be figuring out what is electron flow in this example. What does this voltaic cell look like? Now, if I ask you to do this on a test, I don't expect you to have such a nice sketch, but you should, draw what you think a beaker looks like. Do the best you can. Connect it up. Build me a voltaic cell in terms of what this thing looks like. It is one of the chores that I want you to be able to do. One of the things that I want you to be able to do for this particular chapter. And again, concentrate on the concentration difference. Yes. Again, they're going to meet somewhere in the middle. So this one decreases, that one increases. How do you lose cations in a redox reaction? Well, we want the cation concentration to drop. That means the first half of the voltaic cell is actually going to be the reduction reaction. As this reaction proceeds, as this half reaction proceeds on this side of the concentration cell, well, we're going to consume the zinc cation originally in there, and this concentration is going to drop. Conversely, what happens here? We need to increase the concentration on this side, and the way we do that is we erode away the zinc electrode in this example, and we will increase the zinc cation concentration in this cell. And then again, at some point, they'll reach some middle ground where the voltmeter will shut off. This is the Leo. Now we have enough here. Actually, I do want to put concentration and dilute, because remember, when I look at these two half reactions, number of electrons the same, the metal's the same. The only thing different here is the concentration between the two half cells, and so that's why I need the conc and the deal here to indicate which side is which, and once we combine these to figure out the overall reaction. But the Leo and the Gur that's occurring in this particular example establishes the electron flow. Remember, the oxidation forms the electrons. The electrons are going to flow out. Now I'm connecting it to the voltmeter. If this is the oxidation, then this is the anode. This is the black alligator clip on the voltaic cell. Passes through the voltmeter in the proper way. This is, the voltmeter is designed to, if it receives electrons from the black end, then it's going to give a positive value. Those electrons are allowed to proceed through the voltmeter, and this is where the reduction reaction is going to occur, and that's where the cathode is, and that is going to be the red alligator clip for this process. And as long as you connect it this way, you're going to get a positive value up here. Now, our job is partly this. We've established, what is the anode? Well, for part A in the problem, it's the second half reaction. It's the more dilute one that is acting as the anode. And the next part is to calculate, what is exactly that positive value here for the cell, the concentration cell. And we need two things to do that. Remember, it's the Nernst equation on the previous page. We'll see it again in just a second. Now, since the two half reactions are the same, then the two electrons are equal to the N. It tells us the number of electrons that are passed per reaction here. And then the Q is going to be products over reactants. I'm going to add up these things the same way that I did in the previous example. And what we see is that the let me do the overall reaction up here. Concentration side is the reactant, and then the diluted side is going to represent the product. And then that establishes what the Q looks like for this example. Let's go back to the zinc. Concentration on the bottom, dilute on the top. Very common layout, okay, for these concentration cells. And now, so if we plug in this concentration up top, this concentration at the bottom, actually let me just give this value here. It's 2.78 times 10 to the minus 4. There's a Q value that we will then plug into the Nernst equation. Let me just do remember this drops out at 0. We're still left with a negative sign. Please don't forget that. N is equal to 2, and then the log base 10 for this, for the 2.78 times 10 to the minus 4. If I do this calculation, what I get, it is a spontaneous reaction, which of course it is. Why do I say of course it is? Well, I mean, because there's a concentration difference between the two half reactions. As long as if you have a concentration cell in front of you, something looks like this, same metal for the electrode, same cation in the solution, if there is a concentration difference between the two, it's going to be spontaneous. Okay, so you will get a positive value here. Now, this is certainly a low concentration, but that's really not the point here. The point is, how does this reaction occur? And then, sort of putting the pieces together in terms of what would a voltaic cell look like for a concentration cell. And then ultimately, using that Nernst equation, non-standard conditions, which we certainly have here. It doesn't specify, but you can assume that it's at 298 Kelvin, standard temperature, but it's certainly not standard concentration. These concentrations are far from that, and that's what drives the reaction. Okay? Thanks.